Okay, so this is the third and final lecture on data assimilation. What I want to do with this lecture is actually show you how to implement the data assimilation architecture in practice. And so just want to recall that what we're trying to do is we're thinking about the fact that we have a model, we have some initial conditions as well to that model, and then finally we also have measurements of the system. Let's call this generically, it's represented like this. So we're given a model, we know it's incomplete, we have measurements, we know it's noisy, and we have measurements. This is an initial state estimation, which we know is not quite accurate, and we also have here measurements as we go in time of this system. So the modification of this model, right, is to think about Q1 being some unmodeled physics. I don't have a model for it. I know I have error in my model, and this is just my approximation. And so I'd like to understand the impact on this. Our initial state estimation, instead of being y naught, is actually, there's a noisy measurement, so we're off by some amount, Q2. And then finally, every time we take a measurement, it's not quite accurate. So this is the generic framework for thinking about data assimilation. The error in the model, the error in the initial measurements or initial state of the system to initialize this model, and then of course measurements as we go, and they are in fact noisy measurements. So we talked about last time in the last two lectures, very simple format for both using a vector nature of this and thinking about Kalman filtering. And what we want to do today is actually program it up and show how it works in practice. What we're particularly going to do is, just to sort of highlight the model, is we're going to assume that in fact we have a perfect model. And the model we're going to work with is the Lorenz equation. So we're going to assume I have a perfect model. And what I'm going to assume, though, is that my initial state has some error, Q2. We're going to assume is that we have some kind of random Gaussian noise distribution for the measurement. So we have the measurement plus some random noise, which will be Gaussian. And every time we take a measurement of the system to do our data assimilation, it also will have some measurement error when we take estimates of the system. Okay, so that's going to be the basic framework. So all we care about now is Q2, Q3, and we're going to run a model with imperfect initial data, compare it to measurements, and try to figure out a data assimilation strategy so that we get the best forecast possible given these error metrics. Okay? So I'm going to pull up MATLAB, and we'll start playing within the framework of MATLAB to try to model this phenomena. All right, so let me pull this up here. Pull up our MATLAB. Oop, here we go. There we go. Oop. All right, so here's what our system is. I've pre-programmed up our Lorenz equation. I will run a simulation of this just so you're familiar with it, although we're using it quite extensively in this course as a nice toy model, so hopefully it's fairly familiar to you. And so here's the code. So the code basically is clear all, close all, CLC. I'm going to run it from time 0 to time 20. I'm going to parameterize this with three parameters, sigma. And let me, in fact, I can close this down, push this down there to just have that open. So what we're going to do is we're going to have three parameters. Sigma is 10, B is 8/3, R is 28. So these parameters are typically picked. This is where we get chaotic dynamics in the Lorenz attractor. We're going to specify an initial condition of 5, 5, 5. The initial x, y, and z location are perfectly known at this point. Let's say they're 5 each. And now we can simulate that. So use OD45. You call the right-hand side function, lower underscore right-hand side. You tell it the time you want to solve it for. You give it the initial state. You can prescribe the tolerances here, and then you pass in your three variables. Now what we get out is going to be our truth. We're going to imagine that 555 is actually the state of the system. So this will be our truth measurement. And what we do in simulations is we're not going to be able to get 555. We're going to have some 555 plus some noise on top of that. And that's what's going to make it tough to forecast and actually to match the true solution. The true solution is here. The true x is the first column. True y is the second column. True z is the third column. And then we can plot this. So let's go ahead and do this. First, I will very briefly show you what the right-hand side looks like. Here it is. So the right-hand side of the Lorenz equations is sigma. Here's a quadratic term, x1 plus x, oh sorry, linear term, minus x1, x2. Then we have a quadratic here, x1 times x3, which is the x and the z term, plus rx1 minus x2, and then here's another quadratic term, x1, x2 minus b, x3. So that's the right-hand side. We pass everything in, march it forward in time, and so hopefully everybody's somewhat familiar with how to do that. And so let's just run this thing, see what we get. So when we run it, here's what our simulation produces. It's the classic Lorenz attractor. I think I'm going to try to rotate this so you get a better view. Okay, there we go. All right, so this is, wow, can't see that so well, so let me line width to that thing because I want to make sure we all can get a good view of it, or maybe I can make it just smaller. Okay, come here, and let's put here line width. Oops, cut it off, true. Okay, let's try that. There, that's a little better. There we go. And now I can rotate it. Okay, so this is your trajectories of the Lorenz attractor. You started here at 555. This thing took off and is starting to be on this strange attractor. So this is the dynamical system we want to look at. And part of what we'd like to do is say, well, I would like to follow the trajectories, not just qualitatively, but quantitatively. But the problem is I'm going to have a measurement error on my initial conditions. And so as I go along, we know that this system is very sensitive to initial conditions being off, as I'll show you in a minute. And so we're going to fall off of our trajectory pretty fast. And so what we'd like to do is figure out a way to improve that, and we're going to do the data simulation to do so. Okay, so let's go ahead and close this down. And now that I have this basic code here for solving these things along, what we can start thinking about doing is saying, okay, I want to take this basic architecture, but now I want to run a bunch of initial conditions through it. I already got the true solution. So now let's come here. I'm going to comment first out this code because we don't really need it anymore. And now what we're going to do is make a loop. What we're going to do with this loop is going to produce 8 different initial conditions. So that is our objective right now, is I'm going to go through this 8 times. I'm going to show you, if you hit this with noise, how 8 different viewpoints of this looks like with just a little bit of noise on it, okay? So we're going to take those initial conditions that we had previously, which were the 555, and now we're going to perturb them with a little bit of white noise. Okay, so how to do this? So first we got to decide the strength of our noise. So I'm going to make the noise here, let's call it sigma 2. Remember, this is the variance of that Q2 variable, the Q2, the white noise I'm going to add is going to be given by here. We will make this of strength 1. So strength of noise. Now, here, I'm going to take x naught, which we had up there, and say x naught, okay, the initial conditions to this thing. In fact, let's call this xic for the initial conditions, will be that x naught I had plus rand n with sigma 2 in front of it. And this thing here is 1 by 3. Okay, and we're going to send in now xic. So what I've done here is I've determined the strength of the noise, and we can play around with this. We can make it stronger noise, weaker noise, whatever we want to do. We're going to go through 8 times through the loop. Xic is what the original initial condition was, which was 555, and now I add some random, a random variable to it. And when I go through this, I solve, I'm going to get a solution, and then I'm going to come back through, run it again with a different noise, and I'm going to compare the truth with what I get here. And so to make this comparison easier, I'm just going to look at the x variable and just see how well the x is modeled from this, what happens to the x as a function of time with 8 different noise realizations versus up here, which is the truth of what x should be. Okay? So what we've got to do now is go ahead and come here, and we're going to go ahead and start running this through the system here. So first of all, every time I run this, I want to come here, and I want to plot it. So part of our goal is a subplot for to j. So I'm going to do 8 plots. Okay, and let me make a little more room here for us. So I'm going to make 8 plots here. Each subplot is for one of these different noise realizations. Oops, okay, let me bring that up a little. Okay, so once I get that, then I'll say plot t versus x true. Okay, and we'll make that in, let's say, blue. Actually, let's do magenta. That's going to be the truth solution. And then t versus x sol first column. Let's make that in magenta and green. How's that? And line width 2. Okay, so we're going to go through this thing 8 times, and we're going to compare those against each other. So let's run that. See if this thing here, oh, there we go. Okay, so here is our comparison of these two. So remember, magenta is what it's supposed to be, and green is what my model gives now because my measurement error is slightly off. And in fact, I'm very close to the actual starting value. My noise realization puts me very close to the original x naught, but you can see in these 8 different realizations that in fact, I don't do a very good job in the future state prediction. So just consider this one up here. Look what the magenta is doing compared to the green. Very quickly, I cannot use this green, which is my model with an imperfect initial realization, to do any meaningful prediction of what's going on with the magenta. And you can see that's the case for all of this data here. So this is the problem that we have when we have complex systems where small initial condition perturbations do not allow us to do forecasting in any reasonable manner. And this is a prototype example, which is clearly whatever I have does not do a very good job predicting the future. And what I'd really like to do is make long estimates of the future state and get better forecasting capabilities. And to do that, I've got to figure a way around this issue. What data assimilation is going to do is take measurements occasionally. And once you take those measurements, you're going to update the state of the system relative to what your model is saying versus what your measurement is saying. And remember, the first 2 lectures of this showed you exactly how to use your model prediction with an innovation informed by your error or by your measurement of the system directly to give you a better state estimation. So that's what we're going to do next. So let's go ahead and kill this. And now what we're going to do is build a new model here. And let me come here. Okay. So now what we're going to do is start taking this code and taking it in this direction and start doing some data simulation. So you've seen that I have problems. And so now I'm going to take measurements. So what I did previously is I ran the code. My time step is 0.01. But let's say I have a measurement every half unit of time. Every t equals 0.5. So at 0.5, I'm going to assume that my measurement is the truth plus a little bit of noise. That's going to be determined by my Q3 that we had in the initial data simulation format. And so we're going to have some measurement error. So let's go ahead and build a model for this error. Okay? So what we're going to do, noisy observations. So let's say that what I want is t data, which will be t from 1 to 50 to end. So what have I done here? Remember, my t variable is the OD solver stepped at every 0.01. So every 50 steps of my model is 0.5 units. So that's where I'm going to collect my data. This is where I'm going to assume I have a measurement to help me do the data assimilation portion. Okay? So t data are the measurement times. Okay? Now, the length of this thing, I need it because I'm going to do a loop to go through this, is n. And what I want to do is now start thinking about, I'm going to make 3 variables. At each time step, remember, I have a measurement and I have error at time 0.5, time 1, 1.5, 2, 2.5. So as I go for each one of the variables x, y, and z, I have a measurement error. And so what I want to do is make a vector where I'm going to make a vector of the error I'm going to put onto the actual true measurements at those times. Okay? So here are the vectors. xn, rand n, n by 1. yn is equal to rand n, n by 1. And then z of n equals rand n, n by 1. Okay? So what these are vectors telling me what the error is going to be that I'm going to put on each of the time points. Okay? I can also determine how much noise I want on this thing. Let's say sigma 3 is equal to strength 4. So error. So, or measurement error. So if I have a very good sensor, this 4 would be very small. But if I have a bad sensor, this gets big. So this is the variance of my measurement from the sensor itself. So every time I take a measurement, I know it's imperfect. This number tells me how imperfect it is. Okay. So I'm just picking some numbers here. It doesn't matter so much. You can play around with it later. And so my x data points are x, 1, every step of 50 to the end, plus sigma 3 times xn. So think what I just did. This is now my measurements in x. It's what the truth was, plus sigma 3 xn. Okay? And I got to make sure my truth is still there, so let's go back up here. So this is going to be, so actually I should just use x true. Okay? All right. So it's the truth plus some noise. And I'm going to have one for both x, y, and z. So y data is equal to y true, 150 to the end, plus sigma 3 times yn. And then finally z data equals z true, 150 to the end, plus sigma 3 times yn. So now what I have, these are my measurements. What I'm going to show you really quickly as we run this is I'm just going to plot the actual time series versus where the measurements are. So let's do this for x data versus the truth. So what we can do here is do the following plot. Plot t data versus x data. We're going to put a red circle there. That's where the measurement is. And then we're going to compare that to t versus x true. And we'll make that a black line, line width 2. And let's run that. So now you see what I'm doing. I'm running through this thing. Oops, let's do a new figure here. I'll close the old figure before. So, okay, let's run that. Have the other figure open. Okay, here we go. And out comes this. Okay, so now this is a telling picture. And so this is kind of telling you the story a little bit. And what it's telling you is the black is the truth. So even if you had, and the red is measuring the truth or trying to measure the truth, and it has a certain error. So you can see that the red is off of that black. And again, this is with the sigma equals 4. If you make it smaller, it will shrink down onto the black line, and as you make it bigger, it gets further and further off the black. So the question is the following. I have a model with imperfect initial conditions. I have those red measurements. How can I use the measurements to keep me on this solution? Remember that I fall off of this solution almost immediately. By the time I'm here, if I make that initial condition error that I have, I'm already way off of the solution by the time I get to in this region here, so that my prediction and my model don't agree at all. Okay? But here, what I have the possibility of doing is saying, well, if I have those red measurements, maybe I can simulate the future even if I don't have the right initial data, and so that when I go out into the future, I get a good prediction of that future state, because it's going to be pinned to these red balls. These red dots are telling me that's where the measurement is, so your model better be close to this, or my simulation frame is going to pull it into that. Okay? So let's go ahead and do. Welcome back. That sound you heard was the battery of the microphone going dead. So I'm now here to clean up after yesterday's guy. You know, the dude wearing the paisley purple tie. I mean, who does that? But I'm now going to finish it off, this data simulation lecture. And so apologies, but at least this is a fix-up. So where we left off is I showed you the truth simulation, and I showed you some red dots with where the measurements are. So what I'm going to walk through now is a code that's going to do the data assimilation itself. Okay? So I've actually got the code here, and what I wanted to walk through is just how we're going to construct this. So I want a data assimilated solution. I have measurements, and I have a model prediction. So I have those two, but now I want to integrate them together. So what I'm going to do is come up with a variable called xDA. So this is my x data assimilated solution. So that's what the DA is there for. So I initially started off as being an empty field. I'm going to put nothing in there. And what I'm going to do is I'm going to start to simulate my model for half a unit at a time. The reason I have half a unit is because that's where my measurements are. Every half unit, I actually have a sensor giving me a recording that I can use to change the state of my system, right? So to give me an innovation to what my model says, right? So one way to think about this whole process is I'm going to simulate for a while, reset my state, in other words, restart new initial conditions, run the model again, restart the new initial conditions, and run it again. With the idea that every time I do this, I'm pinning my model back to the measurements. And the hope is that I can make a long time prediction to the future. So here's what I'm going to do. I'm going to do a for loop. 1 to the length of t data minus 1. Now t data are the number of measurements. So presumably when I start at time 0, that's the first measurement, I already have an initial condition, so I don't need to simulate there. I just take my initial measurement and start going forward. So that's why I go t data minus 1. So there's still t data minus 1 points in the future that I got measurements at. And what I'm going to do now is simulate my model for t-span from 0 to time 0.5, and again steps of 0.01. So I'm going to run half a unit out into the future, and so that's what the t-span is. And so I run the OD45 model for half a unit into the future. I go run it, and what I pull out of there is my solution vector, which is now going to be the initial condition. Look like this was what my initial condition would be for my next model run from time 0.5 to 1. And then the next loop would be from 1 to 1.5. And what this initial condition is the last point of this. So it's xsol n1, xsol n2, xsol n3. So that's my x, y, and z positions after running at half a unit in time. Okay? I'm also going to save my data into this xdat file. Remember, this is going to be now take xdat is going to be, I'm going to take, so sorry here. So what I'm going to do here is I'm going to start writing in, this is where my data was collected. Remember that the data file xdat, I'm going to write where my data actually is. So x data, j plus 1, y data, and z data. This is my x, y, and z measurements. Okay, I'm going to say that as xdat. It's a vector with 3 numbers because I'm going to measure x, y, and z at the j plus first point. So remember, I'm going to go through this loop. J is 1, so I'm going to run it out to 0.5. I'm going to go grab that measurement at 0.5. That's the j plus first point. Now here comes the big trick with this, with data simulation. I have measurements, xdat. I have a model prediction, xic naught. Those are the 2 things I have telling me what the solution should look like at 0.5, at time 1, at 1.5, and I want to compare them. So the way the data simulation framework works is by creating the Kalman filter, K, which is the variance of my model divided by the sum of the variance of my model plus the variance of my measurement. And in this case, since they're randomly distributed Gaussian variables with variance sigma 2 and sigma 3, I know exactly what those are, what the K is, so I can compute the Kalman filter directly. Normally in applications, you would actually have to come back and actually do some statistical estimates of your measurements and of your model to compute the variance of the model and the measurements and to compute that quantity there, which is the Kalman filter. Once I have that, then I can say, actually, my initial condition then at time 0.5 or time 1, wherever I'm simulating, is it's xic, which is going to be the initial condition to go back to do a run again, is the value of my model plus Kalman filter times the innovation, which is the difference between my measurement and my model. So if you go back to the previous 2 lectures, this was exactly what we wrote down for the simple example of Kalman filtering. And here it is again here. So it's a 3 vector. My measurement locations and my model locations are the same. And I just improve my model with that innovation, which takes into account the statistics of my measurement error against the statistics of my model error. Okay? Once I get that, I save it. So now, that's my initial condition where I'm going to run it again. But in the meantime, I'm going to save my simulation data xsol. So I'm going to take the xdA, which is my data simulated solution. So xdA is what it was before, and I append to it xsol. All of the rows, in other words, all the time points except for the last one. Why? Because when I go from time 1 to 0.5, I don't need to save 0.5 because time 0.5 is actually the initial point for the next simulation. So I don't want to double count the time slot 0.5 or the time slot 1 or 1.5. I want to actually go ahead and save the data up to just below 0.5, and then the next simulation starts from 0.5 all the way just to below 1, and then from 1 just below 1.5, and then 1.5 onwards. So this XDA is going to include all my data saved at every 0.01 in time, where at every 0.5 units, I take a jump through the data simulation. In other words, I correct where I am with this innovation here. Okay? At the end, I then glue the last point back on. Remember, because I've included everything but the last point, so when I finish the loop, I glue the last point on, and so I have now the solution from time 0 all the way to time 8. And then I can just plot it. Plot the true solution versus the data assimilated solution. Okay? So if I come here, and I can run this model now, this is going to give me, essentially, a time course, which you'll see is going to be my solution. Sorry. Get rid of that. And here it is. So let's talk about this figure here, because now this is, in fact, a model with an assimilated solution. And by the way, every time I run this, it's slightly different because every time I do it has different noise configuration. So if you remember when we did this before, if I just start out with the initial data I had, then my solutions start to fall off right about here. So in other words, there's a big disparity between what the model's telling me and what the true solution is. The true solution here is in magenta. Okay? And so when I'm going to do this data assimilation, I'm going to run it forward in time. And notice I stick onto the solution. There's some spots here where I don't get it right, but then it comes back through a simulation to trying to stick that solution. Now remember, my measurements are every 0.5 units of time. So when something like this diverges in that 0.5 units, it's not clear I can capture it, okay, even with data assimilation. But you can see it can come back. A simulation glues me back onto this attractor, and then I get stuck back onto this thing, and I do pretty well. And of course, I miss some spots. So it's not perfect. But let's do one more simulation of this. So each time I do this, I'm going to get a different thing here. So let's do another one. Geez, look at this one. So here is just a different noise realization, and this one here sticks it, right? Our model with data assimilation is almost perfect. We just stick this thing. So one thing that people do is ensemble Kalman filtering. So I've only shown you one thing here where I just do one trajectory with one realization of noise. What you would actually do in practice is you can do multiple simulations, right, where you add the noise. So and what you do is now you take that ensemble and you look at the average of that ensemble. So here, for instance, if you did a bunch of simulations, look at your data simulated solution, which is the green, which just totally nails the actual truth. So in other words, a simulation framework allows you to go all well into the future and stay onto the exact solution where you would have normally fallen off right about here. Okay, so this becomes a great predictor. But again, this was one trial of the realization. And so what you normally do in practice is you'd run multiple times through the model to get a statistical distribution of what your trajectory should look like, and then you would average that to give you a better indication. So that's ensemble Kalman filtering, and that's something that's commonly used, for instance, in forecasting of atmospheric dynamics. So this is a little simple code. It's pretty powerful in terms of showing you what the data assimilation can actually do for you. And so hopefully if you kind of take something like this, you start to understand how to balance your model and data measurements together to actually get yourself a very good predictor for future state evolution, which is much better than if you just simply take your model alone. And if you just take your measurements alone, then you don't actually have a model. You can't actually do a forecast with just a bunch of measurement points. Here, you're using the measurements, pinning your model to it, forecasting to the future. And that's how that thing works. Okay, hopefully the sound works all the way to the end. And there you got some code to play around with.